In this section, we discuss the multiplicative subgroup of QP, the field of periodic numbers. As before, let U denote the group of invertible elements in ZP. The elements in U are also called the periodic units. For every positive integer, we put UN to be 1 plus p to the power n times ZP. Note that each element in U sub n will have a unique representation 1 plus p to the power n times x for x in ZP. Why is this representation unique? It is unique because, remember, the multiplication by p to the power n in ZP gives an injection. Therefore, if you have a 1 plus p to the power n x equal to 1 plus p to the power n y, then x must be equal to y due to the injectivity. Now we consider the projection of ZP onto its nth component, meaning Z mod PNZ. This guy is also denoted by A sub n. And this projection, with our own notation, is epsilon sub n. If we restrict this epsilon sub n to U, the subgroup of invertible elements in ZP, what do you think the image of U under epsilon sub n is? By the property of ring homomorphism, the image of this homomorphism restricted to the invertible elements will be the invertible elements here. This map is still surjective. And now an interesting question is, what is the kernel of this map? When epsilon sub n is restricted to U. To avoid confusion, at this moment, I'm going to use a more rigorous notation. So this is a restriction of epsilon sub n to U. The kernel of this turns out to be this U sub n we just defined. Now let's check this. One direction is clear. It is clear that U sub n is contained in this kernel. This is because if you take any element in U sub n and you apply the map epsilon sub n to this element, then it's easy to see that this is precisely just 1, because this part has its nth component divisible by p to the power n. So after projection onto the nth component, this part will vanish. So epsilon sub n of 1 plus pnx is just equal to 1. And 1 is the multiplicative identity in Z mod PNZ. So now let's check the other direction. On the other hand, suppose we have element y in the kernel of this, meaning y is in U and epsilon sub n of y is equal to 1. To be rigorous, I should write epsilon sub n restricted to U of y is equal to 1. But the previous writing is also correct. This is also correct, because for epsilon sub n, a map from ZP to AN, its application to y also gives 1. Now, if we think of this in here, and you move this 1 to the left hand side, what we will get is epsilon sub n of y minus 1 is equal to 0 in an. What does this mean? This means y minus 1 is divisible by p to the power n. Or in other words, y minus 1 is a multiple of p to the power n times some element in Zp. And therefore y is equal to 1 plus p to the power n x. And this part follows from our proposition number 1 in this chapter on page 11 of Sayre's book, where we had the short exact sequence. So y minus 1 is in the kernel of this, and therefore must be an image of this. So there exists x in Zp such that y minus 1 is equal to p to the power n times x. Therefore, this epsilon sub n will naturally induce an isomorphism from U mod Un to this multiplex subgroup of Z mod P and Z. As denoted by epsilon sub n tilde from U mod Un to Z mod P and Z star, which is An star. What do we mean by natural here? We mean the following diagram is commutative, and those vertical maps are the canonical transition maps. This diagram is commutative. In particular, if you look at U mod U1, this is isomorphic to Z mod PZ star. This is the multiple group of the finite field with P elements. And it's a cyclic of order P minus 1. This is by theorem 2 on page 4 of Sayre's book. Another observation for those U sub n's is that they will form a decreasing sequence of open subgroups of U. They are clearly decreasing just by the definition of U sub n. This p to the power n times Zp will get smaller and smaller with the increasing n. And this is open because it can be written as an open ball centered at 1 with radius e to the power negative n minus 1. This is something we proved before. Because y in 1 plus p to the power n times Zp, if and only if y minus 1 is in P and Zp, if and only if the p-adic valuation for y minus 1 is bigger or equal to n, if and only if this is strictly bigger than n minus 1, if and only if the distance between y and 1 is strictly less than e to the power negative n minus 1. So this is indeed equal to this open ball. So this is open. And there are subgroups because U sub n is a kernel of the restriction of epsilon sub n to U. So there are also subgroups of U. Now we observe that this U mod UNs together with this transition map will form a projective system. And you may wonder, what is the projective limit of this projective system, or inverse limit? It turns out that the projective limit of the system is isomorphic to U. Now let's check this. The verification is straightforward. You basically just write down the definition of both sides. For the left-hand side, this is a collection of elements, infinite sequences of this infinite product satisfying the compatibility condition. And for the right-hand side, by definition, this is a collection of elements in ZP that are invertible. And written more explicitly, this is the elements in the infinite product of Z mod P and Z that are invertible, and we have the compatibility condition. And the isomorphism from here to here is precisely given by epsilon sub n tilde. This is the isomorphism on individual components. This is because we can rewrite this, the invertible element here, as just the product of invertible elements for individual components. This is because the multiplication here is defined components wisely. So the product of Z mod P and Z star is same as the product of Z mod P and Z star. For each component, U mod UN is mapped isomorphically by epsilon sub n tilde to Z mod P and Z star. So this guy is sent isomorphically to this. And this epsilon sub n also preserves the compatibility here. Why does epsilon sub n tilde preserve the compatibility? This is because of our commutative diagram here. If UN is sent by pi sub n comma n minus 1 to UN minus 1, then the image of UN, which is AN, must be sent correspondingly to the image of UN minus 1 under the map epsilon sub n minus 1 tilde. More formally, if A sub n is equal to epsilon sub n tilde of UN, then phi sub n comma n minus 1 of AN is equal to phi sub n comma n minus 1 of epsilon n tilde of UN. By the commutativity of this diagram, this is equal to epsilon sub n minus 1 tilde composed with this pi sub n comma n minus 1 of UN. And this guy is, by compatibility, UN minus 1. And this guy is, from the structure of this map, equal to AN minus 1. And this verifies the compatibility downstairs. So A sub n is mapped to A sub n minus 1. And this verifies that the inverse limit of u mod un is isomorphic to u. Now let's look at another isomorphism derived from this filtration u sub n. If n is a positive integer, then the map from un mod un plus 1 to z mod pz given by, if an element here is represented by 1 plus pnx, we define the image of this map to be x modulo p. This map is an isomorphism. And now let us check this. To check this, we have to first understand why this map is well defined. This map is well defined because it is induced from this homomorphism. Consider the homomorphism as denoted by capital phi sub n. From u sub n, the multiplicative subgroup, to the additive group z mod pz. By sending an element here, remember by the definition of u sub n is 1 plus pn zp. And an element here can be written uniquely as 1 plus pnx for some x in zp. And we send this element to x mod p, to here. And we need to check why this map is a homomorphism. Namely, why does it turn this multiplication into sum here? So let's check this. Phi sub n of the product 1 plus pnx and 1 plus pny, this is 1 plus pnx plus y plus pnxy. This guy is in zp. And by our definition for phi sub n, the image is supposed to be just x plus y plus pnxy. So image is just this part. And because n is greater or equal to 1, this guy is same as x plus y in z mod pz. So this phi sub n is indeed a homomorphism. And phi sub n is clearly surjective. And now we are interested to know what is the kernel of this. The kernel of this map is, by definition, 1 plus pnx. This is in un, and supposed to be sent by phi sub n to 0 in z mod pz, which means the little x here is divisible by p. So this is the kernel of phi sub n. And this, by definition, because p divides x, so x can be written as a p times of y, where y is in zp. So you can rewrite this as 1 plus p to the power n plus 1 times y, where y is in zp. But this guy is precisely equal to our U sub n plus 1. And this verifies that the kernel is this guy. So this map is an isomorphism. And this verifies this property for the filtration U sub n. Namely, the quotient of two adjacent U sub n's is isomorphic to Z mod PZ, with multiplication in here identified with the addition here. Now, as a consequence, by induction on n, U1 modulo Un has order p to the power n minus 1. Because by isomorphism theorems for groups, this is isomorphic to U1 mod Un plus 1 quotient by Un mod Un plus 1. And you can apply induction here. Finally, let us summarize all the properties that we have obtained in this section. And you can pause here and take a screenshot of this. There are 1, 2, 3, 4, 5 properties for the filtration formed by the subgroups U sub n's.